here's something that should stop you in your tracks. The body you're living in right now, the brain processing these words, the hands you looked at this morning, they're essentially identical to humans who walked the earth 70,000 years ago. Not similar, not roughly the same, virtually indistinguishable. If you could grab one of your ancient ancestors from that era, clean them up, put them in jeans and a t-shirt, they could sit next to you on the subway and no one would look twice. And yet, in those 70,000 years, we went from hunting mammoths with sharpened sticks to splitting atoms and sending robots to Mars. We invented language, writing, mathematics, medicine, the internet. We built pyramids and skyscrapers. We conquered every continent on Earth. But our bodies, our brains, frozen, locked in place, unchanged. For 3,000 generations, human biological evolution has been running on pause, and the reason why might be the strangest twist in the entire history of life on Earth. If you're using this to fall asleep, perfect. That's exactly why I make these. So maybe hit subscribe and tell me in the comments where you are and what time it is. Sydney at dawn, Chicago at midnight, Stockholm during a lunch break. I love seeing this global community scattered across the planet, all curious about the same ancient mysteries. And this particular mystery might be the most personal one we've ever explored together. Because it's not about some distant civilization or forgotten empire. It's about you. The body you're inhabiting right now. The brain that's processing these words at this very moment. The biological machinery that carries you through every single day of your life. That machinery is old, far older than you probably realize, and understanding just how old and why it stopped changing when everything else about humanity kept transforming, well, that's a question that will reshape how you see yourself in the mirror tomorrow morning. Let's start with something concrete, something you can almost reach out and touch. Bones. Human skeletons tell stories that words cannot lie about. When paleoanthropologists excavate remains from different eras of human history, they can measure skull dimensions, analyze bone density, examine the angles of joints and the attachment points of muscles. They can reconstruct with remarkable precision what ancient humans looked like, how they moved, what physical capabilities they possessed, and what those bones reveal is both fascinating and deeply unsettling. In 1967, a team of researchers working in Ethiopia discovered human remains near the Omo River that would eventually reshape our understanding of human origins. These weren't primitive ancestors with sloping foreheads and protruding jaws. These were us. Anatomically modern humans dating back approximately 195,000 years. Their skulls showed the same high, rounded cranial vault we see today. The same flat faces, the same prominent chins. If you placed one of those Omo skulls next to a skull from a person who died last year, the similarities would be striking. The differences would be subtle enough that only a trained expert could identify them, and even then, they'd be working hard to find distinguishing features. But here's where things get genuinely interesting. Go back further in time, to 300,000 years ago, and you start seeing real differences. The Jebel Irhoud remains from Morocco, dating to roughly 315,000 years ago, show humans who were getting close to modern anatomy but weren't quite there yet. Their faces were flatter than earlier hominins, definitely trending in our direction, but their skulls were still elongated, still lacking that distinctive rounded shape we carry today. Evolution was clearly still at work during that period, still sculpting, still refining, still pushing our ancestors towards something new. Now jump forward to 70,000 years ago. Examine the remains from Klaces River in South Africa, or the specimens from Kafsa Cave in Israel dating to around 100,000 years ago. What do you find? Modern humans. Completely, utterly, indistinguishable from people walking the streets of Tokyo or Toronto or Nairobi today. And here's the crucial part that should make you pause. Compare those 70,000-year-old skeletons to skeletons from 10,000 years ago. Then compare those to remains from 5,000 years ago, then to bones from 500 years ago, then to the skeleton inside your own body right now. The differences across all those comparisons are negligible. Statistical noise, natural variation within a stable population, not directional evolutionary change. The transformation stopped. The same pattern emerges with even more clarity when you examine brain size, which is arguably the most important measure of human evolution. For roughly 2 million years, the story of human evolution was largely a story of expanding brains. Our earliest tool-making ancestors, the Australopithecines and early Homo species, had brains roughly 400 to 600 cubic centimeters in volume, about the size of a chimpanzee's brain, maybe slightly larger. Impressive for a primate, but nothing that would suggest world domination was on the horizon. Then something remarkable happened. Brains started growing, and they didn't stop for an incredibly long time. Homo erectus, appearing around 1.9 million years ago, averaged about 900 cubic centimeters of cranial capacity. That's a 50% increase over earlier hominins. Homo heidelbergensis, showing up around 700,000 years ago, pushed past 1,200 cubic centimeters, getting closer to modern territory now. By the time anatomically modern humans emerged somewhere between 300,000 and 200,000 years ago, cranial capacity had reached 1,400 cubic centimeters on average. Some individuals exceeded 1,600 cubic centimeters, larger than most humans alive today. Think about what that trajectory represents. A tripling of brain size over 2 million years. An extraordinary transformation driven by intense, unrelenting natural selection favoring intelligence, social complexity, and problem-solving ability. Every generation, across thousands upon thousands of generations, the individuals with slightly larger, slightly more capable brains had better survival odds. They could make better tools. They could coordinate more effectively with group members. They could anticipate dangers and plan for contingencies. They could remember more, learn faster, teach others more effectively. Over hundreds of thousands of generations, this relentless pressure produced the most complex biological structure in the known universe, the human brain. And then, around 100,000 years ago, give or take, it stopped. Just stopped. Brain size in modern humans has remained essentially constant since that time. Some studies suggest average cranial capacity may have actually decreased slightly over the past 20,000 years, though this finding remains debated among researchers. But what's not debated, what every scientist studying this question agrees upon, is the absence of continued growth. The expansion that characterized millions of years of human evolution simply plateaued and went flat. The engine of neurological evolution, which had been running at full throttle for geological ages, shifted into neutral and has been coasting ever since. The genetic evidence tells the same story, but with even greater precision and detail. Thanks to revolutionary advances in ancient DNA extraction and sequencing over the past 2 decades, scientists can now read the actual genetic code of humans who lived tens of thousands of years ago. They can compare these ancient genomes to modern populations nucleotide by nucleotide, calculating exactly how much genetic change has occurred across the millennia. The results should astonish you. A 45,000-year-old human from Siberia, known to researchers as the Ust-Ishim man after the river near where his remains were discovered, possessed a genome that falls comfortably within the range of modern human genetic diversity. He wasn't a transitional form on his way to becoming fully human. He was fully human, genetically speaking. His DNA would not look out of place in any population alive today. You could sequence his genome alongside 1,000 modern humans from around the world, and statisticians would have trouble picking him out as anything unusual. The same is true for ancient remains from Europe, Asia, Africa, and the Americas, spanning the past 50,000 years. Once you get past a certain threshold in time, roughly 70 to 100,000 years ago, depending on which markers you examine, you're dealing with people who are genetically modern. People whose DNA could theoretically be shuffled into the modern human gene pool without raising any red flags. People who were, in every biological sense that matters, already us. Now consider what this biological stasis means when placed alongside human, cultural, and technological history. Think about everything humanity has accomplished in the past 70,000 years. We went from small bands of hunter-gatherers, perhaps a few dozen individuals following animal herds across savannas and coastlines, to a species of 8 billion that has walked on the moon, split the atom, and connected minds across the globe through invisible electronic signals. We invented agriculture around 12,000 years ago, which allowed us to settle permanently in one place and build villages that became towns, that became cities, that became the sprawling civilizations we inhabit today. We developed writing around 5,000 years ago, preserving knowledge across generations and eventually across millennia. accumulating wisdom in ways no other species has ever achieved. We created art that still moves people to tears after centuries. We composed music that can lift the human spirit or crush it with sorrow. We wrote literature exploring every facet of human experience. We developed philosophy to grapple with questions of meaning and morality. We built science, that extraordinary engine of discovery that has revealed the age of the universe, the structure of atoms, the code of life itself. We invented mathematics, creating an abstract language powerful enough to describe everything from the motion of planets to the behavior of subatomic particles. We built pyramids that have stood for 45 centuries. We erected cathedrals with spires reaching toward heaven. We constructed skyscrapers that dwarf anything nature ever produced. We harnessed electricity and brought light to the darkness. We conquered diseases that had plagued humanity since our origins. We peered into the fundamental structure of matter and found it stranger than any mythology ever imagined. Every single one of these achievements, every breakthrough, every invention, every transcendent work of genius, was accomplished by people working with the same biological equipment as their ancestors who hunted mammoths with sharpened sticks 70,000 years ago. Albert Einstein's brain, the organ that conceived relativity and reshaped our understanding of space and time, was not measurably different in structure or capacity from the brain of an Ice Age human who spent his days tracking antelope across the African savannah, and his nights watching stars he would never understand. William Shakespeare's neurons, which produced language of such beauty that it still echoes 4 centuries later, fired according to the same electrochemical patterns as those of prehistoric hunters who painted animals on cave walls by flickering torchlight. The Wright brothers, who achieved the ancient dream of human flight, possessed no biological advantages whatsoever over humans who had never seen anything fly except birds and had no conception that heavier-than-air flight was even possible. Marie Curie, who unlocked the secrets of radioactivity and became the first person to win Nobel Prizes in 2 different sciences, was running on the same neurological hardware as women who lived 40,000 years ago gathering tubers and nursing infants in temporary camps. This is the paradox at the heart of human existence. And once you see it clearly, you cannot unsee it. We are simultaneously the most rapidly changing force on this planet and the most biologically static large mammal alive. We transform everything we touch. We reshape ecosystems, we redirect rivers and level mountains, we build civilizations that span continents, we create technologies that would seem like magic to our recent ancestors, let alone our distant ones. And yet the biological organism doing all this changing, the creature called Homo sapiens, has remained frozen in evolutionary time for 3,000 generations. How do you reconcile these 2 realities? How do you make sense of a species that is both the most dynamic and the most unchanging thing on Earth? The answer to that question will take us on a journey through catastrophe and survival, through the darkest moment in human prehistory and the strange transformation that emerged from it. Because something happened around 70,000 years ago, something that fundamentally altered the relationship between humanity and evolution itself, something that pressed pause on the biological transformation that had been sculpting our lineage for millions of years and replaced it with something entirely new, something unprecedented in nearly 4 billion years of life on Earth. To understand what that something was, we need to first understand what came before it. We need to see what normal human evolution looked like during the millions of years when evolution was still actively working on us. We need to appreciate the trajectory that was interrupted, the path that was abandoned, the relentless process that suddenly ground to a halt right around the time our ancestors were developing the capabilities that would eventually allow their descendants to ponder questions like this one while lying in bed listening to someone talk about ancient mysteries. So let's go back, way back to a time when evolution wasn't just a background process humming along quietly. It was the dominant force shaping everything about our ancestors, every bone, every organ, every neural pathway. This was an era when being human meant being in constant flux, when the very definition of what a human was kept changing generation after generation, millennium after millennium for millions of years without pause. To truly appreciate how strange our current biological stasis is, you need to understand just how dynamic human evolution used to be. Imagine watching a time-lapse video of the past 3 million years of human evolution compressed into a few minutes. What you'd see would look almost like a special effect. Skulls morphing and reshaping, faces flattening, foreheads rising, bodies stretching and restructuring, brain cases inflating like balloons, an entire lineage in constant motion, never settling into a stable form, always becoming something different from what it was before. That's what normal looks like for a species under evolutionary pressure, and humans were under some of the most intense evolutionary pressure any mammal has ever experienced. Let's start with the brain, because that's where the most dramatic transformation occurred. 3 million years ago, our ancestors were creatures called Australopithecines. You've probably heard of Lucy, the famous fossil discovered in Ethiopia in 1974. Lucy was an Australopithecus afarensis, a small-bodied hominin who walked upright but still had a brain roughly the size of a chimpanzee's. Around 400 cubic centimetres, maybe 450 if she was lucky. Enough to navigate the African savanna, find food, avoid predators, maintain social relationships within a small group, but nothing that would suggest her descendants would one day build particle accelerators and compose symphonies. Now follow the trajectory forward. Around 2.8 million years ago, something started shifting. A new lineage emerged, one we call Homo habilis, the handyman. These creatures had slightly larger brains, around 600 to 700 cubic centimetres on average. Still small by modern standards, but noticeably bigger than what came before. And crucially, they were making stone tools, deliberately selecting rocks with certain properties, striking them at specific angles to produce sharp flakes that could cut meat and scrape hides. This was technology, primitive by our standards, but revolutionary in its time. Then came Homo erectus, appearing around 1.9 million years ago, and this is where the brain expansion really kicks into high gear. Homo erectus brains averaged around 900 cubic centimetres. Some individuals exceeded 1,000. That's more than double the brain size of Australopithecines, achieved in less than 2 million years. In evolutionary terms, that's extraordinarily rapid change. Something was driving brain expansion with tremendous force, selecting ruthlessly for intelligence generation after generation. And Homo erectus didn't just have bigger brains, they used them. These were the first hominins to leave Africa, spreading across Asia and into Europe. They mastered fire perhaps as early as 1 million years ago, fundamentally transforming their relationship with the environment. Fire meant warmth in cold climates. It meant protection from predators at night. It meant cooked food, which is easier to digest and releases more nutrients, potentially fueling further brain growth. Homo erectus developed more sophisticated tools than their predecessors, including hand axes that required genuine skill and foresight to manufacture. For over 1 million years, Homo erectus was the most successful hominin on the planet. But evolution didn't stop with them. It never stops. Around 700,000 years ago, new forms began emerging. In Europe, a population we call Homo heidelbergensis appeared, likely descended from Homo erectus populations that had migrated north. Their brains were larger still, averaging around 1,200 cubic centimetres. They were physically robust, powerfully built to handle the demands of hunting large game in challenging environments. From Homo heidelbergensis, 2 remarkable lineages would eventually branch. In Europe, isolated by glacial cycles that repeatedly cut populations off from the rest of the world, a distinct species evolved that we know as Neanderthals. In Africa, a parallel population continued evolving toward what would eventually become anatomically modern humans. And somewhere in Asia, another lineage was quietly developing, one we wouldn't even know existed until 2010 when geneticists identified them from a finger bone found in a Siberian cave. The Denisovans. Think about what this means. For hundreds of thousands of years, multiple human species walked the Earth simultaneously. This wasn't a neat linear progression from primitive to advanced. It was a branching bush, with different human populations evolving different solutions to survival challenges in different environments. Neanderthals developing stocky, cold-adapted bodies to survive European ice ages. Denisovans spreading across Asia, with adaptations we're still working to understand. Small-bodied humans like Homo floresiensis evolving on isolated Indonesian islands. Their brains shrinking as their bodies miniaturized in response to limited island resources. The human family tree was crowded with cousins, most of whom would eventually go extinct. And through all of this, brains kept getting bigger. Neanderthals actually had slightly larger brains than modern humans on average, around 1,400 to 1,600 cubic centimetres. Their brains weren't shaped exactly like ours. The proportions were different, with larger visual processing areas and differently structured frontal lobes, but in sheer volume they matched or exceeded us. These were intelligent, capable beings. They made sophisticated tools. They buried their dead with apparent ritual. They created art, or at least symbolic markings that suggest something like artistic thinking. They survived ice ages that would have annihilated less capable creatures. The Denisovans remain more mysterious because we have so few fossils, but genetic evidence suggests they were similarly sophisticated. They interbred with both Neanderthals and modern humans, meaning all three species recognized each other as close enough to be potential mates. They spread across an enormous geographic range, from Siberia to Southeast Asia, and they left genetic gifts in modern human populations, including altitude adaptation genes that still help Tibetans survive at high elevations today. But brains weren't the only thing changing during this long epoch of evolutionary transformation. Everything was in flux. Skeletal structures were constantly being reshaped by natural selection. Early hominins had bodies adapted for climbing trees and walking on the ground, a compromise between two different modes of locomotion. Over millions of years, our lineage became increasingly committed to bipedalism, with changes rippling through the entire skeleton. Pelvises widened and reshaped to support upright walking efficiently. Spines developed curves that balanced the body over 2 legs instead of 4. Leg bones lengthened relative to arms. Feet transformed from grasping appendages into rigid platforms designed for pushing off the ground. Each of these changes took thousands of generations to complete, with natural selection favouring individuals whose anatomy worked slightly better for walking and running across open landscapes. The changes weren't always improvements in every sense. Human childbirth became dramatically more difficult as brain size increased, while the pelvis could only widen so much without compromising walking efficiency. This is why human infants are born so helpless compared to other mammals. They have to emerge before their heads get too large to fit through the birth canal. It's an evolutionary compromise, a trade-off between big brains and functional bipedalism, and it happened because evolution doesn't plan ahead. It just responds to immediate pressures, sometimes creating problems while solving others. Teeth and jaws were also in constant flux during this period. Early hominins had large molars and powerful jaws for processing tough plant foods. As tool use allowed our ancestors to process food externally, cutting meat with sharp stones and later cooking it with fire, the selection pressure for massive chewing apparatus relaxed. Teeth got smaller, jaws became more gracile, faces flattened. The protruding muzzle that characterized earlier hominins gradually retreated until it became the flat face we recognize as human. You can trace these changes through the fossil record with remarkable precision. Measure the thickness of tooth enamel across different hominin species and time periods. Compare the size of molar teeth relative to body mass. Examine the attachment points for chewing muscles on fossil skulls. What you find is continuous change, not stability. Every few 100,000 years, the dental morphology of the human lineage shifted measurably. Jaws became less robust, teeth became smaller. The entire craniofacial architecture was being remodeled by natural selection, responding to changing diets and food processing technologies. Tool technologies themselves reflect this constant evolutionary flux, not genetic evolution directly, but cultural evolution that was tightly linked to biological capabilities. The earliest stone tools, from around 3.3 million years ago, were crude implements barely distinguishable from naturally broken rocks. Over hundreds of thousands of years, toolmaking became more sophisticated. Homo erectus developed the Acheulean tradition, characterized by carefully shaped hand axes that required foresight and skill to produce. These hand axes remained the dominant tool technology for over 1 million years, an almost unimaginably long time by modern standards. But they did change subtly over that span, becoming more symmetrical, more refined, more standardized. Around 300,000 years ago, new toolmaking techniques emerged. Instead of shaping a single hand axe from a rock core, toolmakers began preparing cores in ways that allowed them to strike off multiple sharp flakes with predetermined shapes. This was more efficient, producing more cutting edge per pound of raw material. It required more cognitive sophistication, more planning, more understanding of how stone fractures under pressure. Different human populations, Neanderthals in Europe, early modern humans in Africa, developed variations on these prepared core techniques independently, suggesting the cognitive capacity for this kind of technological innovation was spreading through multiple hominin lineages. The point of all this detail is to establish a baseline. This is what evolution looks like when it's operating normally on a lineage. Constant change, bodies reshaping, brains expanding, new species branching off and adapting to different environments. Tools becoming more sophisticated as the minds using them become more capable. Millions of years of transformation, with no generation looking quite like the one that came before. No century passing without measurable change accumulating in bones and genes and artifacts. If you could somehow observe human evolution from outside, watching it unfold over millions of years like a scientist observing bacteria in a petri dish, you would see a lineage in perpetual motion, never static, never stable, always being pushed and pulled by environmental pressures, by competition, by the relentless logic of differential reproduction. The individuals who survived slightly better passed on their traits. Those traits accumulated. The species changed, again and again and again, for millions upon millions of years. This was the normal state of human evolution. This was what it meant to be a hominin for the vast majority of our lineage's existence. Change was constant. Stasis was unthinkable. The idea that human evolution might simply stop, that the same body plan might persist unchanged for 70,000 years, while everything else about human life transformed beyond recognition, this would have seemed impossible based on the previous 3 million years of evidence, and yet that's exactly what happened. Something occurred around 70,000 years ago that interrupted this trajectory. Something that pressed pause on millions of years of biological change and replaced it with a completely different kind of evolution. Something that made the human body essentially freeze in place, while the human mind and human culture began changing faster than anything evolution had ever produced. To understand what that something was, we need to travel to an island in Southeast Asia, to a mountain that doesn't look particularly threatening today, to an event so catastrophic that it nearly erased humanity from existence entirely, an event that would fundamentally transform what it meant to be human and set the stage for everything that came after. The island is Sumatra, the westernmost major island of Indonesia. Today it's home to dense rainforests, endangered orangutans, and millions of people going about their daily lives. Tourists visit its beaches, farmers tend their crops, cities bustle with the ordinary rhythms of modern life, but hidden in the northern part of the island lies a scar so enormous that you can see it from space. Lake Toba, one of the largest volcanic lakes on Earth, stretching roughly 100 kilometers long and 30 kilometers wide. It's beautiful in that postcard way that tropical lakes can be, surrounded by green hills, dotted with fishing boats, popular with visitors seeking mountain coolness away from the lowland heat. Most people who visit Lake Toba have no idea they're standing inside a wound that nearly killed our entire species. 74,000 years ago, give or take a few millennia based on dating uncertainties, this spot was not a lake. It was a mountain, or more precisely, a cluster of volcanic peaks sitting atop one of the most dangerous geological features on the planet, a supervolcano, a magma chamber so vast and so pressurized that when it finally released, it produced an eruption almost beyond human comprehension. This was the Toba catastrophe, and nothing in the past 2 million years has come close to matching its destructive power. Let's talk about scale, because the numbers here are important for understanding what our ancestors faced. When Mount St. Helens erupted in 1980, it was considered a major volcanic event. It killed 57 people, flattened hundreds of square kilometers of forest, sent ash across 11 states, and dominated news coverage for weeks. The eruption ejected roughly 1 cubic kilometer of volcanic material into the atmosphere. 1 cubic kilometer. Remember that number. The Toba eruption ejected approximately 2,800 cubic kilometers of material, 2,800 times more than Mount St. Helens. This is not a difference of degree. This is a difference of kind. This is the difference between a firecracker and a nuclear weapon. This is an explosion so vast that the human mind struggles to process what it actually means. Picture it this way. If you took all the ash and rock and pumice that Toba ejected and spread it evenly across the continental United States, it would bury the entire country under roughly 2 feet of volcanic debris. Every city, every farm, every forest, every mountain covered in a thick grey blanket of death. That's how much material this single eruption produced, and unlike a bomb that detonates in one instant, this catastrophe unfolded over days or weeks, a sustained release of destruction that just kept coming and coming and coming. The immediate blast zone would have been annihilated instantly. Everything within several hundred kilometers of the eruption, vaporized, incinerated, buried under hundreds of feet of pyroclastic flow, those superheated avalanches of gas and rock that travel at speeds exceeding 100 kilometers per hour. Nothing survives pyroclastic flows, not animals, not plants, not bacteria. The land itself is sterilized down to the bedrock, but the immediate blast zone was just the beginning. The ash clouds spread outward from Sumatra, carried by winds across the Indian Ocean, across the Arabian Sea, across the Bay of Bengal. Within days, ash was falling on India, on Southeast Asia, on East Africa. Layers of Toba ash have been found in sediment cores from the Arabian Sea, from the South China Sea, from the Indian subcontinent. In some locations in India, ash deposits from this single eruption exceed 6 meters in thickness. 6 meters of volcanic ash, falling from the sky like grey snow, covering everything, killing everything it touched. And the ash was toxic. Volcanic ash isn't like wood ash, or the ash from a campfire. It's composed of tiny fragments of volcanic glass, sharp-edged particles that shred lung tissue when inhaled. Animals caught in the ashfall would have suffocated, their lungs filling with microscopic shards that lacerated the delicate tissues meant for extracting oxygen from air. Plants would have been buried, their leaves covered by deposits too heavy to shake off, unable to photosynthesize, dying by the billions. But even the ashfall wasn't the worst part. The true horror of Toba came from what happened to the atmosphere. When a supervolcano erupts, it doesn't just throw rock into the sky. It injects massive quantities of sulfur dioxide and other gases into the stratosphere, the layer of atmosphere that sits above the weather systems we experience at ground level. Up there, above the clouds, above the rain that might wash particles back to Earth, these gases undergo chemical reactions that produce sulfuric acid aerosols, tiny droplets of sulfuric acid suspended in the upper atmosphere, forming a haze that spreads around the entire planet. And this haze does something terrifying. It reflects sunlight back into space before it can reach the surface. It blocks the energy that warms the Earth, that drives the weather, that powers the photosynthesis that feeds every food chain on the planet. When enough sulfuric acid accumulates in the stratosphere, the world goes dark and cold. Climate scientists call this a volcanic winter. The term is chillingly appropriate. In the months following the Toba eruption, global temperatures plunged. Different models produce different estimates, but the consensus suggests average temperatures may have dropped by 3 to 5 degrees Celsius globally. In some regions, particularly at higher latitudes, the drop was much more severe, perhaps 10 degrees, perhaps 15. In a matter of months, the planet went from interglacial warmth to near Ice Age conditions. Now, 3 to 5 degrees might not sound catastrophic if you're thinking about weather, the difference between a pleasant spring day and a slightly cool one. But we're not talking about weather, we're talking about climate, about average temperatures across seasons and years. A 3 to 5 degree drop in global average temperature transforms ecosystems. It kills forests, it extends ice sheets, it changes rainfall patterns across entire continents. It takes environments that were marginal for survival and makes them uninhabitable. And this cold didn't last for a season. The volcanic winter persisted for somewhere between 6 and 10 years, decade after decade of diminished sunlight. Growing seasons shortened or eliminated entirely. Plant communities that had sustained herbivore populations for millennia suddenly producing a fraction of their normal biomass. Prey animals starving, then dying, then disappearing from territories where they had been abundant for countless generations. For the humans alive during this catastrophe, the world they knew was simply ending. Not metaphorically, literally. Everything they had learned about survival, every piece of knowledge passed down through hundreds of generations, all of it was becoming useless. Think about what this means in concrete terms. You're a human living in East Africa 74,000 years ago. Your people have occupied this territory for generations beyond counting. Your grandparents taught your parents the location of every water source, every reliable hunting ground, every stand of fruiting trees. This knowledge is survival itself. It's encoded in stories, in place names, in the rhythm of seasonal movements that your band has followed since before memory began. Then the sky changes colour. At first it might seem strange, but not alarming. Maybe a haze on the horizon, maybe unusual clouds. Then ash starts falling, fine grey particles that coat the leaves and fill the water holes. The air smells wrong, acrid, chemical. Animals start behaving strangely, migrating out of season, congregating in unusual places, dying for no apparent reason. And then the cold comes. Not the normal cool of nighttime or the dry season, but a bone-deep chill that settles over the land and refuses to lift. Mornings that should be warm dawn grey and frigid. The sun, when visible through the haze, seems weak, distant, wrong. Plants that should be flowering are withering instead. The fruit trees that your people have depended on for generations are producing nothing, their leaves yellowed and falling. The game is disappearing. The antelope herds that you tracked across the savannah are gone. Moved south perhaps, or simply dead. The small animals you trapped for supplementary protein have vanished into burrows and won't come out. The fish in the rivers are floating belly up, killed by ash contamination, or temperature changes, or the collapse of the aquatic food chains they depended on. And winter arrives early and lasts longer than any winter in living memory. Then it doesn't really end. The following summer is not quite summer, more like an extended autumn that never quite warms. Frosts come at times when frosts have never come before. More plants die. More animals disappear. The cycle of scarcity intensifies with each passing season. You don't know what's happening. You can't know. You have no framework for understanding volcanic eruptions on the other side of the planet, stratospheric sulfuric acid, global temperature fluctuations. All you know is that the world is dying around you, and you have no idea if it will ever stop. This is the psychological dimension of the Toba catastrophe that raw numbers can't capture. Yes, the statistics are staggering. 2,800 cubic kilometers of ejecta, global temperature drops of 5 to 15 degrees, a volcanic winter lasting most of a decade. But behind those numbers were real humans, people with families and fears and hopes, watching everything they knew crumble into ash and cold. The genetic evidence suggests that what followed was devastation on a scale that nearly ended the human story entirely. Populations that had spread across Africa and possibly into Asia and Europe were hammered down to almost nothing. Small bands that had managed to find refugia, locations where conditions remained barely survivable, clung to existence by the thinnest of margins. In many regions, human populations simply disappeared, not leaving enough survivors to contribute to the genetic legacy of modern humanity. How do you survive something like this? The honest answer is that most people didn't. The archaeological record from this period shows abandoned sites, interrupted cultural sequences, gaps in habitation that suggest entire regions becoming uninhabitable. The humans who survived were the lucky ones, the ones who happened to be in the right place, who happened to have access to resources that didn't completely fail, who happened to make the right decisions at the critical moments when death was one bad choice away. They survived by eating things they never would have eaten before, by moving to territories their ancestors had never explored, by abandoning traditions that no longer worked in a world where the old rules had been erased. They survived by being flexible when flexibility was the only thing that could save them, by being innovative when innovation meant the difference between one more meal and starvation, by being cooperative when cooperation meant pooling dwindling resources with other desperate survivors. The people who made it through Toba weren't the strongest or the fastest. They were the ones who could adapt when adaptation was everything, the ones who could look at a transformed world and find new ways to extract survival from hostile conditions, the ones who could maintain social bonds under pressure, who could share knowledge rapidly, who could solve unprecedented problems without the luxury of trial and error across generations. In other words, they were the ones whose brains could do something that brains hadn't really needed to do before. Not just learn from the environment, but learn from each other at speeds that evolutionary time couldn't match. Not just adapt to circumstances, but innovate new solutions in real time. Not just remember what worked in the past, but imagine what might work in a future that looked nothing like anything that came before. The Toba catastrophe didn't just reduce human populations, it filtered them. It selected for traits that would have been useful in any environment, but became absolutely essential in the post-apocalyptic world that emerged from the volcanic winter. It created conditions where the cognitive and social capabilities that would later define humanity became not just advantageous, but mandatory for survival. And the survivors, those few thousand individuals who made it through the decade of darkness, they would become the ancestors of every human being alive today. Their genes would become our genes. Their traits would become our traits. The adaptations that saved them would define us 70,000 years later, still running on the biological hardware that emerged from the greatest catastrophe our species ever faced. But how do we know any of this actually happened? How can scientists peer back 74,000 years and tell us with confidence that humanity nearly went extinct? We weren't there. Nobody wrote anything down. The survivors left no monuments, no inscriptions, no records of their desperate struggle. They were too busy trying not to die to document their experience for future generations, who might want to understand what they went through. The answer lies in a kind of evidence that's even more reliable than written records. It's evidence that can't be forged, can't be embellished, can't be distorted by the biases of whoever recorded it. It's evidence written into every cell of your body, encoded in the molecular structure of your DNA, passed down through an unbroken chain of reproduction, spanning 3,000 generations from those ancient survivors to you. Your genes tell the story of what happened to your ancestors, and the story they tell about the period around 74,000 years ago is absolutely terrifying. Let's start with mitochondrial DNA, because it provides one of the clearest windows into our past. Unlike the nuclear DNA that contains most of your genetic information and comes from both parents, mitochondrial DNA is inherited exclusively through the maternal line. You got your mitochondrial DNA from your mother. She got hers from her mother got hers from her mother, and so on, stretching back through an unbroken chain of mothers and daughters to the very beginning of our species. Mitochondrial DNA also mutates at a relatively steady rate, accumulating small changes over time like a molecular clock. By comparing the mitochondrial DNA of people from different populations around the world, geneticists can work backward, calculating when various lineages split apart and estimating the size of the ancestral population at different points in the past. It's like reconstructing a family tree, but instead of names and dates, you're using mutations and statistical models. When researchers first conducted these analyses in the 1980s and 90s, they found something that shocked the scientific community. All human mitochondrial DNA traces back to a remarkably recent common ancestor, a woman who lived in Africa somewhere between 150,000 and 200,000 years ago. The media dubbed her Mitochondrial Eve, though the name is somewhat misleading because she wasn't the only woman alive at the time, just the only one whose mitochondrial lineage survived to the present day. But more striking than the recency of our common ancestor was what the analysis revealed about population sizes. The patterns of variation in human mitochondrial DNA suggested that at some point in our past, the human population had contracted dramatically. The diversity was too low, the lineages too closely related to have come from a large, stable population. Something had pruned the human family tree down to a fraction of its former size. Y chromosome analysis told the same story from the paternal side. The Y chromosome passes from father to son, just as mitochondrial DNA passes from mother to daughter. When geneticists examined Y chromosome variation across human populations, they found the same signature of a severe bottleneck. All human Y chromosomes trace back to a common male ancestor who lived roughly the same time period as mitochondrial Eve, give or take some tens of thousands of years depending on the analysis method. And the nuclear DNA, the vast majority of our genetic material that contains the genes, for everything from eye colour to disease susceptibility, confirmed what the mitochondrial and Y chromosome data suggested. Human genetic diversity is remarkably low, startlingly, unnaturally low in ways that demand explanation. Consider this comparison. There are roughly 300,000 chimpanzees living in the wild today, scattered across equatorial Africa in fragmented populations. There are 8 billion humans spread across every continent on Earth. You would expect humans, with our vastly larger population size, to have far more genetic diversity than chimpanzees. More individuals should mean more genetic variation, more different versions of genes circulating in the population. The reality is the opposite. Chimpanzees have significantly more genetic diversity than humans. A single community of chimpanzees in a single forest in Tanzania contains more genetic variation than all of humanity combined. This is not what you would expect from a species that numbers in the billions and has been around for 200,000 years. This is what you would expect from a species that nearly went extinct. The mathematics of population genetics allow scientists to estimate just how small the human population must have become to produce our current levels of genetic diversity. The models converge on a figure that should make you uncomfortable. Somewhere between 3,000 and 10,000 breeding individuals. That's not total population, that's breeding population, the individuals who are actually reproducing and passing genes to the next generation. The total population, including children, elderly individuals, and those who didn't reproduce, might have been somewhat larger, but even generous estimates suggest humanity was reduced to a few tens of thousands at most, 3,000 to 10,000 people, on the entire planet. Let that sink in for a moment. That's smaller than the population of most small towns. It's smaller than the student body of many universities. It's fewer people than attend a typical professional baseball game. The entire future of humanity, everyone who would ever live, every civilization that would ever rise, every achievement that would ever be accomplished, all of it hung by a thread held by a population you could fit into a single sports stadium. And this wasn't spread evenly across the globe. The genetic evidence suggests survivors were clustered in refugia, isolated pockets where conditions remained barely tolerable during the worst years of the volcanic winter. Probably a few locations in East Africa, possibly some coastal areas in southern Africa, where marine resources provided an alternative food source when terrestrial ecosystems collapsed. Maybe small groups scattered elsewhere who would eventually die out or be absorbed into the main surviving population. These survivors were isolated from each other, separated by vast distances of uninhabitable territory. They likely had no idea that other groups existed, no knowledge that humans were clinging to survival in other refugia hundreds or thousands of kilometers away. Each group would have felt utterly alone, the last people in a dying world. The bottleneck lasted for an extended period, probably thousands of years. It wasn't a single bad season that populations bounced back from quickly. It was a sustained reduction in human numbers lasting long enough to permanently reshape the human gene pool. Multiple generations were born, lived, and died during this period of minimum population. The bottleneck wasn't just deep, it was wide, lasting long enough for its genetic effects to become fixed in the population. What does a bottleneck like this actually do to a species? The consequences are profound and permanent, affecting genetic diversity, disease susceptibility, evolutionary potential, and even psychological traits for thousands of generations afterward. First, the most obvious effect, massive loss of genetic variation. Before, Toba, the human population probably contained millions of individuals, each carrying their own unique combinations of genetic variants, accumulated over hundreds of thousands of years of evolution. Different populations in different regions would have developed different adaptations to local conditions. There would have been substantial variation in physical traits, disease resistance, cognitive characteristics, and countless other features encoded in DNA. The bottleneck erased most of this variation in a single catastrophic event. When 95% or more of a population dies, they take their genes with them. Every unique genetic variant carried only by individuals who died is lost forever. Every adaptive trait that hadn't yet spread widely through the population disappears. Every potential evolutionary pathway that depended on genes present only in the victims is permanently closed off. Think of it like a library fire. Before the fire, the library contains millions of unique books representing centuries of accumulated knowledge. After the fire, only a few thousand books survive, randomly distributed across what used to be a comprehensive collection. The surviving books aren't necessarily the best or most important ones. They're just the ones that happen to be in the parts of the library that didn't burn. Entire subjects are now unrepresented. Knowledge that took generations to accumulate is gone forever. The genetic bottleneck worked the same way. The variants that survived weren't necessarily the best or most adaptive ones. They were just the ones that happened to be carried by the individuals who made it through, who happened to be in the right refugia, who happened to make the right decisions, who happened to have enough luck to survive when almost everyone else died. This random element of survival is what geneticists call genetic drift, and in small populations it becomes extremely powerful. In a large population, random chance tends to average out. A genetic variant might increase slightly in one generation due to chance, then decrease slightly in the next. Over time, these random fluctuations cancel each other out, and natural selection becomes the dominant force shaping which genes become more or less common. But in a tiny population of a few thousand individuals, random chance dominates. A genetic variant can become common or go extinct purely through luck, regardless of whether it's beneficial or harmful. This means the survivors of Toba didn't necessarily carry the best human genes. They carried a random sample of genes, filtered through the chaos of catastrophe, shaped as much by accident as by adaptation. Some researchers have suggested that certain features of modern human genetics, traits that seem poorly designed or maladaptive, might have become fixed in our species not because they were beneficial, but simply because they happened to be present in the bottleneck survivors. We may carry genetic baggage that natural selection would have eliminated in a larger population, but became universal simply because everyone who didn't carry it happened to die for reasons unrelated to those particular genes. The bottleneck also created what geneticists call founder effects. When a large population is reduced to a small number of survivors, and those survivors then give rise to all subsequent generations, the genetic quirks of those specific individuals become disproportionately important. Any unusual variants they happen to carry become much more common in the descendant population than they would have been otherwise. This is why certain genetic diseases are more common in populations that went through historical bottlenecks. Ashkenazi Jews, for example, show elevated rates of several genetic disorders because their ancestral population was quite small at certain points in history, and the founders happened to carry variants for those conditions. The Toba bottleneck was vastly more severe than any bottleneck in recorded human history, affecting our entire species rather than a single ethnic group. But perhaps the most profound consequence of the bottleneck was what it did to the relationship between humans and evolution itself. The survivors weren't just any humans. They were humans who had proven capable of surviving unprecedented catastrophe. They were humans who could adapt when adaptation was everything, who could cooperate when cooperation meant sharing the last scraps of food with others who might otherwise be competitors, who could innovate when innovation meant the difference between finding one more meal and starving to death. The bottleneck didn't just reduce genetic diversity, it concentrated certain traits related to cognitive flexibility, social intelligence, capacity for rapid learning and teaching. These weren't luxuries anymore. They were absolute requirements for survival. Anyone who lacked them died. Anyone who possessed them had a chance, just a chance, of making it through to the other side. And when the volcanic winter finally ended, when the skies cleared and temperatures began to rise and ecosystems slowly recovered, the humans who emerged were not quite the same as the humans who had gone in. They were fewer in number, yes. They were less genetically diverse, certainly. But they carried within them the seeds of something that had never existed before. The capacity for a new kind of evolution entirely. One that didn't depend on random mutation and natural selection playing out over geological time, one that could transform in generations rather than millennia. The catastrophe had forged something new, and that something was about to change everything. But before we explore what emerged from the ashes, we need to understand the crucible itself. Because the Toba bottleneck wasn't a random filter that simply reduced human numbers through blind chance. It was a selection event of extraordinary intensity, a decade-long examination that tested every aspect of human capability and found most of humanity wanting. The survivors weren't just lucky. They were the ones who possessed specific combinations of traits that allowed them to endure when endurance seemed impossible. To understand what those traits were, we first need to understand where survival was even possible. The volcanic winter didn't affect the entire planet equally. Some regions became completely uninhabitable, their ecosystems collapsing entirely under the weight of ashfall and temperature drops. Other regions, while severely stressed, retained enough resources to support small populations of humans who knew how to exploit them. These refugia, these sanctuaries of survival, would become the cradles of all subsequent humanity. The genetic and archaeological evidence points to two primary regions where human populations likely persisted through the worst years. The first was the East African highlands, particularly areas in what is now Ethiopia, Kenya, and Tanzania. These elevated regions would have experienced cooling like everywhere else, but their tropical latitude meant temperatures remained above the threshold for total ecosystem collapse. The altitude actually provided an advantage in one respect. Populations already adapted to highland conditions were accustomed to cooler temperatures, and would have experienced the volcanic cooling as less of a shock than lowland tropical populations. The East African Rift Valley, with its chain of lakes and diverse microclimates, probably offered multiple pockets where survival remained marginally possible. Fish populations in the lakes would have declined but not disappeared entirely. Highland forests would have contracted but not vanished completely. The region's extraordinary biodiversity, the result of millions of years of complex geological and climatic history, provided a buffer against total collapse that simpler ecosystems couldn't match. The second major refugium was likely the southern African coastline, particularly the region around what is now South Africa. Coastal environments offered something that inland areas couldn't: access to marine resources, shellfish, seaweed, fish, marine mammals. These food sources operate on different ecological cycles than terrestrial plants and animals. While inland herbivores were starving as vegetation died back, coastal populations could harvest mussels and limpets from rocky shores, collect kelp and other edible seaweeds, and exploit the relatively stable productivity of coastal waters. Archaeological sites along the South African coast show continuous human occupation spanning the Toba period. Places like Pinnacle Point and Blombos Cave contain evidence of humans exploiting marine resources with increasing sophistication during exactly the time frame when inland populations would have been struggling to survive. These coastal foragers weren't just scraping by, they were developing new technologies, new strategies, new ways of extracting sustenance from an environment their ancestors had never fully exploited. The coastline refugium theory helps explain something that has puzzled researchers for decades: why the earliest evidence of behavioral modernity, the sophisticated stone tools, the shell beads, the ochre processing, seems to cluster in southern Africa during the period immediately before and after Toba. The traditional explanation was that these innovations arose randomly and then spread. But perhaps the causation runs the other way. Perhaps the coastal refugium selected for the kinds of cognitive traits that produced these innovations. Perhaps the humans who survived were the ones capable of this kind of creative adaptation, and their descendants carried those capabilities forward. But having access to a survivable refugium wasn't enough by itself. The humans who made it through Toba needed more than just a fortunate location. They needed specific capabilities that allowed them to exploit that location effectively while their world fell apart around them. Think about what survival during the volcanic winter actually required. Your traditional food sources are failing. The plants you've gathered for generations are dying or not fruiting. The animals you've hunted are gone, migrated, dead. The water sources you've relied on are contaminated with ash, or have dried up as precipitation patterns shift. Everything your parents and grandparents taught you about surviving in this environment is becoming useless because the environment itself has transformed into something unrecognizable. In this situation, what traits determine who lives and who dies? Physical strength helps, but only to a point. Yes, stronger individuals can travel farther in search of food, can fight off competitors, can endure physical hardship longer. But the volcanic winter wasn't a brief crisis where toughing it out for a few weeks made the difference. It lasted years, possibly decades. Physical strength depletes over time without adequate nutrition. The strongest individual in the group might survive the first year through sheer metabolic reserves. But by year 3 or year 5, pure physicality isn't enough anymore. Speed and agility, similarly limited in value. These traits help when you're chasing prey or fleeing predators, but when prey animals have vanished from your territory and predators are starving along with everything else, being able to run fast doesn't feed your children. What actually mattered was something less visible than muscle mass or running speed. What mattered was what was happening inside the skull: cognitive flexibility, the ability to abandon strategies that weren't working and try something completely different. The capacity to look at a resource you've never exploited before and figure out how to make use of it. Humans who were rigidly committed to traditional hunting methods died when the game disappeared. Humans who could shift to gathering shellfish, processing new plant foods, exploiting previously ignored resources, these were the ones who found enough calories to keep themselves and their families alive. This kind of flexibility isn't just about intelligence in the abstract sense, it's about a specific cognitive capacity, the ability to inhibit established behavioral patterns and substitute novel ones. Your brain has spent your entire life learning that you hunt antelope in this valley during this season. Every instinct, every habit, every automatic behavioral program is geared toward that strategy. Cognitive flexibility means being able to override all of that and do something completely different when the situation demands it. Social intelligence was equally critical, perhaps more so. No individual human, no matter how cognitively flexible, could survive the volcanic winter alone. The challenges were too great, the margins too thin, the knowledge required too vast for any single mind to contain. Survival required groups that could coordinate their efforts, share information, pool resources, and maintain cooperation even when resources were desperately scarce. This is harder than it sounds. When food is abundant, cooperation is easy. There's enough for everyone, so sharing costs you little. But when food is scarce, when every calorie you share with someone else is a calorie your own children don't eat, cooperation becomes genuinely costly. The temptation to hoard, to steal, to prioritize your immediate family over the broader group becomes overwhelming. The groups that survived were the ones that somehow maintained cooperation through the darkest years. Groups where individuals continued sharing information about food sources, even when that information was valuable enough to provide competitive advantage. Groups where hunters shared meat, even when keeping it all would have meant their own children ate better. Groups where the sick and injured were cared for rather than abandoned, perhaps because the group recognized that anyone might be sick or injured tomorrow and would need that same care. This kind of sustained cooperation requires sophisticated social cognition, the ability to recognize reciprocity, to remember who has cooperated in the past and who has cheated, to build trust through repeated interactions, to communicate intentions clearly enough that coordination is possible. It requires what psychologists call theory of mind, the capacity to model what other individuals are thinking and feeling, to predict their behavior, to understand their needs well enough to negotiate mutually beneficial arrangements. Innovation capacity completed the triad of survival traits. The volcanic winter wasn't a static challenge. Conditions kept changing as the crisis unfolded. The strategies that worked in year 1 might fail in year 3 as resources shifted and ecosystems continued transforming. Survival required not just abandoning old strategies, but generating new ones, creating solutions to problems that no human had ever faced before. This is where we see the emergence of something truly remarkable in the archaeological record. The period during and immediately after Toba shows an acceleration of technological innovation that had no precedent in earlier human history. New tool types appear. Bone tools, which require different manufacturing techniques than stone tools, become common for the first time. Composite tools, implements made from multiple materials joined together, show up in the record. Processing techniques for extracting nutrients from previously inedible foods proliferate. These innovations weren't random mutations that happened to spread. They were solutions to urgent problems, generated by minds under extreme pressure to find new ways of surviving. The humans who couldn't innovate, who couldn't look at a problem and imagine a novel solution, died. The humans who could innovate, who could see possibilities where others saw only obstacles, lived long enough to pass on whatever genetic and cultural factors enabled that innovation. And here's the crucial point that connects everything. These 3 traits, cognitive flexibility, social intelligence, and innovation capacity, aren't separate capabilities. They're interconnected aspects of a single cognitive architecture. The kind of brain that can flexibly abandon failing strategies is also the kind of brain that can model other minds effectively, which is also the kind of brain that can generate novel solutions to unprecedented problems. The Toba bottleneck didn't select for 3 independent traits. It selected for a particular kind of mind, a mind optimized for rapid adaptation through learning and social coordination, rather than slow adaptation through genetic evolution. A mind capable of cultural evolution at speeds that biological evolution could never match. The survivors who emerged from the refugia after the volcanic winter ended weren't just a smaller version of pre-Toba humanity. They were a concentrated version, refined by the most intense selection event our species had ever experienced. Every one of them carried the cognitive architecture that had proven essential for survival. Every one of them was capable of the flexibility, the social coordination, the innovative problem-solving that had made the difference between life and death. And when those survivors began reproducing again, when the human population started recovering from its catastrophic low point, they passed those traits to their children, who passed them to their children, who passed them to their children, generation after generation, for 3,000 generations, all the way down to you. This is what geneticists mean when they talk about founder effects. The specific characteristics of a bottleneck population become locked into the descendant population because everyone who comes after inherits from that limited pool of founders. Before Toba, there was presumably more variation in human cognitive architecture. Some populations might have been more socially sophisticated, others more individually innovative, others more cognitively flexible. The bottleneck eliminated most of that variation, leaving only the individuals who combined all three capabilities at levels sufficient for catastrophic survival. We are all descendants of those survivors. Every human being alive today, all 8 billion of us spread across every continent and every culture, traces back to that handful of cognitive elites who made it through the volcanic winter. Their particular configuration of mental capabilities became our species' standard equipment. The template they established in those desperate millennia became the template for all subsequent humanity. This is why humans today are so remarkably similar in our basic cognitive architecture despite our surface diversity. We all possess theory of mind. We all have the capacity for flexible problem solving. We all can learn from others and transmit knowledge to others. These aren't variable traits that differ dramatically between populations. They're universal human features, present in every neurologically typical individual regardless of culture or ancestry. They're universal because they had to be. Because everyone who lacked them died in the volcanic winter, and everyone who came after inherited from the survivors who possessed them. The bottleneck didn't just reduce humanity's numbers, it standardized humanity's minds, creating a species with a remarkably uniform cognitive foundation upon which all subsequent cultural variation would be built. The crisis was over, the crucible had done its work, and the humans who emerged from it were about to discover that they possessed capabilities their ancestors could never have imagined. Something extraordinary happened in the millennia following the Toba catastrophe, something that shows up in the archaeological record like a sudden flash of lightning illuminating a landscape that had been dark for eons. Around 70,000 years ago, human behavior transformed in ways that had no precedent in the previous 3 million years of hominin evolution. It was as if a switch had been flipped inside the human mind, activating capabilities that had been dormant or underdeveloped for hundreds of thousands of years. Scientists call this transformation the emergence of behavioral modernity, but that clinical term doesn't capture what actually happened. What happened was that human beings became fully human in the sense we would recognize today. They started doing things that only humans do. Things that separate us from every other species that has ever existed. Things that would eventually lead to everything from cave paintings to quantum physics, from burial rituals to space exploration. The archaeological evidence for this transformation is stunning in its clarity and its abruptness. Before 70,000 years ago, the artifacts humans left behind are relatively simple and remarkably consistent across vast stretches of time and space. Stone tools from 200,000 years ago look essentially identical to stone tools from 150,000 years ago. The same basic designs, the same manufacturing techniques, the same limited repertoire of implements. Change happened, but it happened at a glacial pace, barely perceptible even across spans of thousands of years. Then, starting around 70,000 years ago, and accelerating rapidly in the millennia that followed, the archaeological record explodes with innovation and diversity. Suddenly you see tools that had never existed before. Bone points and awls, crafted from a material that requires completely different techniques than stone. Compound tools combining multiple components, like stone blades hafted onto wooden handles with plant resin or animal sinew. Microliths, tiny precision-made stone blades designed to be fitted together into composite implements. Standardized tool types that appear across sites separated by hundreds of kilometers, suggesting shared cultural traditions and possibly direct exchange between distant groups. But tools were just the beginning. The real revolution was in what those tools represented and what else appeared alongside them. Art. For the first time in the human record, you see objects that serve no practical purpose whatsoever. Pieces of ochre engraved with geometric patterns, cross-hatched lines carved into mineral surfaces through deliberate, time-consuming effort, shell beads, tiny marine shells collected far from the ocean, pierced with holes, strung together as ornaments. These beads appear at sites in southern Africa, dating to around 75,000 years ago, and they represent something profound. Humans were now creating objects whose value was entirely symbolic. A shell bead doesn't help you hunt. It doesn't keep you warm. It doesn't protect you from predators. Its value exists only because humans collectively agree it has value. Its meaning made physical. Personal ornamentation implies something else that's easy to overlook: identity. When you wear a distinctive necklace, or paint your body with ochre, in particular patterns, you're communicating something about who you are. You're signaling group membership, social status, individual personality. You're participating in a shared symbolic system where everyone understands what these decorations mean. This requires not just the ability to create symbols, but the ability to read them, to understand that others are sending signals through their appearance, to maintain complex mental models of social identity that go far beyond simple face recognition. The archaeological record also shows the emergence of long-distance trade networks during this period. Materials start appearing at sites hundreds of kilometers from their geological sources. Obsidian from volcanic regions shows up in settlements far from any volcano. High-quality stone, suitable for toolmaking, travels vast distances from its origins. Marine shells appear at inland sites that are weeks of walking from the nearest coast. This trade couldn't have happened without language sophisticated enough to negotiate exchanges with strangers, to agree on values, to coordinate the logistics of moving goods across vast distances. It implies social networks extending far beyond the immediate band, relationships maintained with groups you might see only occasionally, perhaps once a year or even less frequently. It implies trust, the ability to enter into agreements with people you don't know well and have confidence they'll be honoured. And this brings us to the revolution beneath all the other revolutions: language. Not simple communication, which plenty of animals possess, but fully modern human language with all its extraordinary capabilities. Vervet monkeys have different alarm calls for different predators. One call means eagle, another means leopard, another means snake. That's impressive, but it's not language. It's a fixed set of signals with fixed meanings, unable to express anything beyond its predetermined repertoire. Honeybees perform dances that communicate the direction and distance of food sources. Also impressive, but still not language. The dance can only convey information about one specific topic using one specific format. Human language is something categorically different. It's generative, capable of producing infinite novel sentences from a finite set of elements. You can combine words in ways no one has ever combined them before and be understood. You can talk about things that don't exist, events that happened in the past, possibilities that might occur in the future, abstract concepts that have no physical presence at all. You can lie. You can tell stories. You can explain your reasoning and invite others to critique it. Language is recursive, meaning you can embed structures within structures indefinitely. The cat sat on the mat. The cat that chased the mouse sat on the mat. The cat that chased the mouse that ate the cheese sat on the mat. There's no limit in principle to how complex these embedded structures can become. This recursive property allows human language to express ideas of arbitrary complexity, limited only by the memory and attention of speaker and listener. Most importantly, language is a tool for thought itself. It's not just a way of communicating ideas that already exist fully formed in your mind. It's a way of constructing ideas, of combining concepts in novel ways, of reasoning through problems by manipulating symbols. When you think through a complex problem, you're often using language internally, talking to yourself in a very real sense. The ability to string words together into chains of reasoning gives you cognitive capabilities that would be impossible without linguistic symbols to think with. We don't know exactly when fully modern language emerged. Language doesn't fossilize, but everything in the archaeological record from around 70,000 years ago onward suggests that humans had crossed a linguistic threshold. The complexity of the behaviours, the evidence of planning and coordination, the symbolic systems in art and ornamentation, the trade networks spanning hundreds of kilometres, none of this makes sense without sophisticated linguistic capability. Something had unlocked in the human capacity for language, and that something changed everything. Here's what's crucial to understand about all these changes. They weren't genetic evolution in the traditional sense. The humans who started making shell beads 75,000 years ago weren't genetically different from humans who hadn't made shell beads a few thousand years earlier. Their DNA was essentially the same. Their brains were the same size. The biological hardware hadn't changed significantly. What changed was software. What changed was culture. The cognitive architecture that emerged from the Toba bottleneck, the particular configuration of flexibility, social intelligence, and innovative capacity that had been essential for surviving the volcanic winter, turned out to be capable of something that no biological system had ever achieved before. It could evolve without genetic change. It could adapt and improve and transform through learning, rather than through the slow, bloody process of differential reproduction. Think about how biological evolution works. A beneficial mutation appears randomly in one individual. If that individual survives and reproduces more successfully than others because of the mutation becomes slightly more common in the next generation. If it keeps providing survival advantages, it keeps spreading, generation after generation, until eventually it becomes universal in the population. This process takes thousands of generations at minimum. For major adaptations, it takes hundreds of thousands of years. Cultural evolution works on a completely different timescale. Someone invents a better way of making a stone tool. They show it to their children, their siblings, their friends. Those people show others. Within a few years, the entire local population is using the new technique. Within a few decades, it might spread across an entire region. Within a few centuries, it could span a continent. And unlike genetic evolution, cultural evolution is Lamarckian, meaning acquired characteristics can be passed on. You don't have to be born knowing how to make the better tool. You can learn it during your lifetime and teach it to others. This is the cheat code humanity discovered. For nearly 4 billion years, life on Earth had been adapting to environmental challenges exclusively through genetic evolution. New capabilities required new genes. New genes required random mutations that happened to be beneficial. The process was slow, wasteful, limited by the pace at which mutations occur and spread. Species that couldn't evolve fast enough to match changing conditions went extinct. The fossil record is littered with the remains of organisms that lost the evolutionary race. Then along came a species that figured out how to sidestep the whole system. Instead of waiting for beneficial mutations to arise and spread through differential reproduction, humans could generate beneficial innovations through thought and spread them through teaching. Instead of adapting over thousands of generations, humans could adapt within a single lifetime. The bottleneck had concentrated the cognitive traits that made this possible, and now those traits were producing exactly what they were capable of producing. The implications were revolutionary, though nobody at the time could have understood what was happening. When a human group developed a new technique for extracting water from plant roots during a drought, that technique could spread through the entire population within years. When someone figured out a better way to treat animal hides to make warmer clothing, that knowledge could transmit to neighbouring groups through trade and intermarriage. When a storyteller composed a particularly effective narrative for teaching children about dangerous plants or animals, that story could propagate across hundreds of kilometres and persist for thousands of years. Knowledge was becoming cumulative in ways it had never been before. Each generation could start with everything the previous generation had learned and build upon it. Innovations didn't have to be reinvented repeatedly. They could be preserved, refined, and expanded. The ratchet of cultural accumulation started clicking forward, and unlike biological evolution, it never clicked backward. Knowledge gained was knowledge kept, passed down through the generations in an ever-growing inheritance. This is why human evolution effectively stopped around 70,000 years ago. Not because there was anything wrong with our genes, or because natural selection ceased to operate. Evolution stopped being the primary driver of human adaptation because something better had emerged. Something faster, something more powerful, something that could accomplish in years what evolution required millennia to achieve. The humans who walked out of Africa around 60,000 years ago, spreading across the planet to colonize every habitable environment, from Arctic tundra to tropical rainforest, weren't adapting to those new environments through genetic evolution. They were adapting through culture. They invented clothing for cold climates, boats for crossing water, new hunting techniques for unfamiliar prey, new gathering strategies for unfamiliar plants. They carried their adaptations with them in their minds and their traditions rather than in their chromosomes. The mind had awakened. And the awakened mind had discovered that it didn't need evolution anymore. It could evolve itself faster and better than blind natural selection ever could. The age of biological humanity was ending. The age of cultural humanity had begun. And once that transition happened, once culture became humanity's primary adaptation mechanism, the old rules of evolution stopped applying to us. Not completely, not in every way, but in the ways that matter most. The relentless pressure that had shaped our ancestors for millions of years, sculpting their bodies and brains through the brutal calculus of differential survival and reproduction, lost most of its power over our species. Natural selection didn't disappear entirely, but it was demoted from the driving force of human change to a minor background process, still operating but no longer determining the trajectory of humanity. To understand why this happened, you need to appreciate the fundamental speed mismatch between biological evolution and cultural evolution. They operate on timescales so different that comparing them is almost like comparing the movement of continents to the movement of cars on a highway. Biological evolution is slow, painfully, almost incomprehensibly slow by human standards. A beneficial genetic mutation arises in a single individual. If that individual is lucky enough to survive and reproduce, they might pass the mutation to a few of their children. Those children, if they're also lucky, might pass it to a few of their children. Generation by generation, if the mutation keeps providing survival advantages, it gradually becomes more common in the population. How long does this take? For a strongly advantageous mutation in a small population under intense selection pressure, we're talking about hundreds of generations at minimum. For more typical mutations with modest advantages in larger populations, thousands of generations. For complex adaptations requiring multiple coordinated genetic changes, tens of thousands of generations or more. At roughly 25 years per human generation, a moderately beneficial trait might take 50,000 years to spread through a population. A complex adaptation might take hundreds of thousands of years. Cultural evolution operates on an entirely different clock. Someone figures out a better way to do something. They show it to the people around them. Those people show others. Within years, perhaps within months, the innovation can spread through an entire local population. Within decades, it can cross regions. Within centuries, it can span continents. And unlike genetic evolution, where the rate of spread is limited by reproduction, cultural evolution can spread as fast as humans can communicate. Consider what this speed difference means in practical terms. Imagine a population of humans facing a new environmental challenge, say a climate shift that makes their traditional food sources scarce. Under purely biological evolution, they would need to wait for random mutations that help them exploit alternative food sources. Those mutations would need to arise, prove beneficial, and spread through the population over hundreds or thousands of generations. If the climate shift was severe enough, the population might go extinct before evolution could catch up. Under cultural evolution, the same population could develop new foraging strategies, new hunting techniques, new food processing methods within a single generation. The individuals who figured out solutions could teach others directly. Within years, the entire group could be exploiting resources that their grandparents had never touched. The adaptation happens fast enough to match the pace of environmental change, which biological evolution almost never can. Once humans crossed the threshold, where cultural evolution became fast enough to solve survival problems before biological evolution could respond, the old selection pressures started losing their grip. Why would natural selection favour individuals with genetic adaptations for cold tolerance when anyone could learn to make warm clothing? Why would it favour individuals with specialised digestive systems when anyone could learn to cook food into more digestible forms? Why would it favour individuals with particular sensory capabilities when anyone could learn to make tools that extended human senses far beyond their biological limits? This is where technology enters the picture, not as a mere convenience but as a biological substitute. Every significant technology humans developed removed or reduced a selection pressure that had previously been shaping human evolution. Take clothing. For millions of years, hominin populations expanding into colder climates faced intense selection pressure for physiological cold tolerance. Neanderthals evolved stocky bodies with shorter limbs to conserve heat, larger nasal passages to warm cold air before it reached the lungs, and presumably various metabolic adaptations for generating and retaining body heat. These adaptations took hundreds of thousands of years to develop, and they tied Neanderthals to cold environments where their specialized physiology was advantageous. Modern humans took a different path. Instead of waiting for evolution to produce cold-adapted bodies, they invented tailored clothing. Animal hides cut and sewn to fit the body closely, trapping air for insulation, protecting skin from wind and moisture. With good clothing, a human with a tropical body plan could survive Arctic conditions indefinitely. The genetic pressure for cold tolerance essentially disappeared overnight. There was no longer any survival advantage to evolving Neanderthal-like cold adaptations because anyone could simply put on warmer clothes. Fire worked the same way, but even more profoundly. Fire extended the habitable temperature range for humans far beyond what any biological adaptation could achieve. Fire allowed cooking, which externalized part of the digestive process, breaking down tough plant fibers and tough meat before it even entered the body. Cooked food releases more calories and nutrients than raw food, and it's easier to chew and digest. This reduced selection pressure for powerful jaws and large teeth, for long digestive tracts, for metabolic adaptations related to processing raw foods. The archaeological evidence shows this clearly. Human teeth and jaws became progressively smaller over the past few 100,000 years, and this reduction accelerated after the control of fire became universal. Our digestive systems are shorter than those of other great apes, optimized for the easily digested cooked foods that became our species' staple diet. We didn't evolve these features because they were inherently superior. We evolved them because fire removed the selection pressure for the alternative, and biological structures that aren't under selection pressure tend to atrophy over evolutionary time. Tools extended this pattern across virtually every domain of physical capability. Sharp stone tools meant humans didn't need sharper teeth or stronger claws. Throwing spears and later bows and arrows meant humans didn't need faster legs or stronger arms for hunting. Containers for carrying water meant humans didn't need the camel's ability to survive long periods without drinking. Shelters meant humans didn't need the physiological hardiness to survive exposed to the elements. Every tool was a selection pressure neutralized. Every technology was a step away from biological adaptation and toward cultural adaptation. The cumulative effect, compounding over thousands of years, was to remove humans from the evolutionary pressures that continued shaping every other species on the planet. But technology wasn't the only force weakening natural selection in human populations. Something else was happening, something that might be even more significant in the long run. Humans were developing social systems that actively protected individuals who would have been eliminated by natural selection in any other species. In the wild, natural selection is brutal and efficient. An animal born with a genetic defect that impairs its ability to find food, escape predators, or compete for mates will usually die before reproducing. Its defective genes die with it. This is how evolution maintains the fitness of populations, by continuously removing genetic variants that reduce survival or reproductive success. But humans started breaking this rule surprisingly early in our history. Archaeological evidence shows Neanderthals caring for severely injured individuals who survived for years, despite disabilities that should have been quickly fatal. A Neanderthal skeleton from Shanidar Cave in Iraq shows a man who had lost the use of one arm, probably from childhood, and was blind in one eye. He lived to be around 40 years old, a remarkable age for a Neanderthal. Someone was feeding him, protecting him, caring for him through decades of life when he couldn't fully care for himself. Modern humans took this even further. The archaeological record from the period after Toba shows increasing evidence of individuals surviving into old age, living decades beyond their peak physical capabilities. It shows healed injuries that would have been fatal without extended care. It shows individuals with congenital abnormalities who survived to adulthood. The genetic defects that would have been ruthlessly eliminated in other species were being preserved in human populations because humans were actively keeping affected individuals alive. This is compassion, and from a moral perspective it represents one of humanity's noblest traits. The willingness to care for those who cannot care for themselves, to expend resources on individuals who cannot reciprocate, to value human life beyond its immediate utility. But from an evolutionary perspective, compassion is profoundly disruptive. It fundamentally breaks the mechanism by which natural selection improves genetic fitness. When you keep individuals with harmful genetic variants alive long enough to reproduce, those variants stay in the gene pool. They don't get selected out, they accumulate. Over hundreds of generations, variants that would have been eliminated in any other species persist in human populations, maintained by cultural systems of care that override biological imperatives. This doesn't mean humans were degenerating or becoming less fit in any simple sense. The harmful variants that accumulated were being compensated for by cultural adaptations. Poor eyesight? Make corrective lenses. Weak immune system? Develop medical treatments. Physical disability? Create assistive technologies. The cultural solutions were more than adequate to offset the genetic costs, which is precisely why the genetic costs were allowed to accumulate in the first place. But it did mean that natural selection was losing its power to shape human biology. The filter that had been refining human genes for millions of years was developing enormous holes. Genetic variants that would have been eliminated within a few generations in a pre-cultural species could now persist indefinitely, carried through the generations by individuals whose survival depended on cultural rather than genetic adaptations. The agricultural revolution, beginning around 12,000 years ago, intensified all of these trends dramatically. Agriculture produced food surpluses that could support individuals who contributed nothing to food production. Cities created environments so different from anything in humanity's evolutionary past that most evolved traits became irrelevant to survival. Specialized labor meant you didn't need to be good at everything. You just needed to be good enough at one thing to trade for everything else you needed. By the time civilizations emerged, natural selection had become almost irrelevant for human populations. Nearly everyone who survived infancy could expect to live to reproductive age. Nearly everyone who reached reproductive age could find some way to reproduce, regardless of their genetic fitness by any traditional evolutionary measure. The differential survival and reproduction that drives natural selection had been almost completely eliminated by cultural systems that buffered individuals from environmental pressures. This is the world we inherited. A world where biological evolution has essentially stopped shaping humanity in any significant way. A world where the genetic lottery of birth matters less and less because cultural systems can compensate for almost any biological disadvantage. A world where the body you're living in, the brain processing these words, is essentially the same as bodies and brains from 70,000 years ago, frozen in evolutionary time while everything else about human existence has transformed beyond recognition. Natural selection didn't die completely. It still operates at the margins, still affecting traits that cultural systems can't fully compensate for. But it lost the war against culture tens of thousands of years ago. The engine that shaped all other life on Earth was defeated by something it had never encountered before, a species that could evolve without changing its genes. But how can we be certain this actually happened? How do we know that human biological evolution really stopped rather than simply slowing down or shifting in ways we haven't detected? The answer is that we have evidence, hard, physical, measurable evidence preserved in fossils and ancient DNA that tells a story so clear it's essentially undeniable. The bones don't lie, the genomes don't lie, and what they tell us confirms everything we've been exploring together. Let's start with skulls, because skulls preserve better than almost any other part of the skeleton, and they contain the most information about the traits that matter most for understanding human evolution. Brain size, facial structure, jaw shape, dental morphology, all of it is encoded in the skull's architecture. When paleoanthropologists excavate ancient human remains, the skull is often the most valuable find. A time capsule containing detailed information about what humans looked like and how they were changing at that particular moment in history. The story skulls tell about human evolution is one of dramatic transformation followed by sudden stasis. Go back 315,000 years to the site of Jebel Irhoud in Morocco. The skulls discovered there represent some of the earliest known members of our species, Homo sapiens in its most archaic form. These were humans, but they wouldn't look quite right to modern eyes. Their skulls were elongated front to back, lacking the rounded globe shape characteristic of later humans. Their faces projected forward more than ours do. Their brow ridges were more prominent, forming a continuous bar of bone above the eyes rather than the smooth forehead we see today. If you measured their cranial capacity, you'd find brains within the modern range, around 1,300 cubic centimeters, but housed in a differently shaped container. Now jump forward about 120,000 years to the Omo remains from Ethiopia, dating to approximately 195,000 years ago. Something has clearly changed. The skulls are more rounded, the faces are flatter, the brow ridges are less prominent. These individuals would still look slightly unusual to modern eyes, but the differences are subtle. The trajectory toward modern anatomy is unmistakable. Evolution is clearly at work, generation after generation, reshaping the human skull towards something more familiar. Continue forward to around 100,000 years ago, to sites like Kafse and Skul in what is now Israel. Here we find humans who are essentially anatomically modern. Their skulls could be placed alongside skulls from any modern population and would not stand out as unusual. High rounded cranial vaults, flat faces beneath smooth foreheads, prominent chins, reduced brow ridges, the modern human form had arrived. And then something remarkable happens in the fossil record. It stops changing. Compare those 100,000-year-old skulls from Kafse to skulls from 50,000 years ago. Then compare those to skulls from 20,000 years ago, then to skulls from 10,000 years ago, then to skulls from people who died last century. The differences between any of these samples are negligible, falling within the range of normal variation you'd find within a single modern population. Statistical analysis cannot reliably distinguish ancient modern human skulls from contemporary ones based on shape alone. The morphological evolution that had been transforming human skulls for hundreds of thousands of years simply plateaued. This isn't a matter of incomplete fossil evidence or dating uncertainties. We have enough specimens from enough time periods that the pattern is unmistakable. Dramatic change before 100,000 years ago. Stasis after 100,000 years ago. The trajectory that had been reshaping human anatomy for millions of years went flat and stayed flat. Brain size tells the same story with particular clarity. For over 2 million years, increasing cranial capacity was perhaps the most consistent trend in human evolution. From the roughly 450 cubic centimeters of Australopithecus to the roughly 900 cubic centimeters of Homo erectus, to the roughly 1,200 cubic centimeters of Homo heidelbergensis, to the 1,400 cubic centimeters of modern humans, brains just kept getting bigger. Every few 100,000 years, average brain size increased measurably. The pressure for intelligence was relentless, and the biological response was consistent expansion of the organ that produces intelligence. Then, around 100,000 years ago, the expansion stopped. Modern human brain size averages between 1,300 and 1,400 cubic centimeters, with individuals ranging from roughly 1,100 to 1,600, depending on body size and normal population variation. This range has been stable for at least 100,000 years, possibly longer. The ceiling was reached and never exceeded. Some studies suggest that average human brain size has actually decreased slightly over the past 20,000 years or so. This is a controversial finding, and the magnitude of the decrease is debated. But multiple analyses have found that Upper Paleolithic humans, the cave painters and mammoth hunters of Ice Age Europe, had somewhat larger average brain volumes than contemporary populations. If true, this would mean the one consistent trend in millions of years of human evolution not only stopped, but reversed, at least slightly. How do we explain this? If bigger brains were advantageous for millions of years, why did they stop being advantageous? The answer connects to everything we've been discussing. Bigger brains became less necessary once cultural evolution could accomplish what biological evolution had previously been required for. The cognitive capabilities that bigger brains provided, better problem solving, more effective social coordination, enhanced learning and memory, could now be achieved through cultural systems rather than biological enhancement. You don't need a bigger brain to know more if you can store knowledge externally in language, stories, and eventually writing. You don't need enhanced individual memory if your group maintains collective memory through oral traditions. You don't need greater individual problem-solving capacity if you can pool cognitive resources through cooperation and communication. Cultural technologies effectively extended human cognitive capabilities without requiring any increase in biological brain tissue, and brain tissue is expensive. The human brain consumes roughly 20% of the body's energy while comprising only about 2% of its mass. Maintaining a larger brain requires more calories, which in evolutionary terms means more foraging effort, more competition for food, higher risk of starvation during lean times. When the benefits of larger brains could be achieved through cultural means, the selection pressure maintaining large brains weakened, and the energetic costs may have started favouring slightly smaller, more efficient brains instead. But fossils can only tell us so much. They reveal external anatomy, bone structure, cranial capacity. They can't tell us directly about the genes that produce those structures, about the underlying molecular machinery of inheritance. For that, we need ancient DNA. The ability to extract and sequence DNA from ancient remains has revolutionized our understanding of human evolution over the past 2 decades. What seemed impossible when the first complete human genome was sequenced in 2003 has become almost routine. Recovering genetic information from bones and teeth that are tens of thousands of years old, reconstructing the genomes of individuals who died before agriculture, before civilization, before anything we would recognize as history. And what ancient DNA reveals about human evolution is extraordinary. It confirms at the molecular level everything the fossils have been telling us. The oldest complete human genome yet recovered comes from a femur bone found near the Ostishim River in Siberia. The individual died approximately 45,000 years ago, during a period when modern humans were still spreading out of Africa and encountering Neanderthals and Denisovans across Eurasia. His DNA was extracted, sequenced, and compared to modern human populations. The results were striking. The Ostishim man's genome falls comfortably within the range of modern human genetic diversity. He carried roughly the same amount of Neanderthal DNA as non-African populations today, indicating that the interbreeding between modern humans and Neanderthals had already occurred by his time, and the Neanderthal contribution to our genome was already approximately what it remains today. His genes, examined 45,000 years after his death, would not stand out as unusual if found in a living person. Similar results have emerged from other ancient genome studies. A 37,000-year-old individual from Kostenki in Russia, 40,000-year-old remains from Romania, 30,000-year-old specimens from across Europe. Again and again, the pattern is the same. Genetically modern humans, their DNA falling within the variation we see in living populations, already fully human in every genetic sense that matters. When geneticists calculate the rate of evolutionary change by comparing ancient genomes to modern ones, they find very little directional change. Random genetic drift has shuffled variation around. Migration and mixture have moved genes between populations, but the kind of systematic, selection-driven change that would indicate ongoing biological adaptation is largely absent. The genes for brain development, for body structure, for the fundamental architecture of the human organism, these have remained remarkably stable for tens of thousands of years. The ancient DNA also reveals something fascinating about the timing of human genetic diversity. Most of the genetic differences between modern human populations arose relatively recently, within the past 50,000 years or so, as humans spread across the globe and adapted to local conditions in minor ways. But the core human genome, the genetic blueprint that defines our species, was already established before that dispersal. The humans who left Africa 60,000 years ago were already carrying essentially the same genes we carry today. Everything that's happened since has been rearrangement and minor adjustment, not fundamental change. If you're finding this journey through human evolution fascinating, take a second to hit that like button and drop a comment telling me where in the world you're watching from right now. I genuinely love checking those comments, seeing messages from Tokyo, from Lagos, from Buenos Aires, from 1,000 different places, all exploring these same ancient questions together. It reminds me we're all part of this same strange, improbable human story, all descendants of those bottleneck survivors, all carrying the same genetic legacy through whatever corner of the planet we happen to inhabit. The convergence of evidence from fossils and ancient DNA presents a picture that's difficult to dismiss. Skull shapes that stopped changing 100,000 years ago, brain sizes that plateaued around the same time, genomes from 45,000 years ago that are essentially indistinguishable from modern ones. Every line of evidence points to the same conclusion. Human biological evolution effectively ceased tens of thousands of years ago. This doesn't mean absolutely nothing has changed. There are minor adaptations, which we'll explore in the next chapter. Adjustments to diet, to disease, to local conditions that have left small genetic signatures in particular populations. But these are footnotes to the main text. The fundamental human genome, the the biological blueprint that makes us Homo sapiens, reached its current form before the pyramids, before agriculture, before civilization, before humans even finished spreading across the planet. We are living in bodies designed by evolution for conditions that haven't existed for 70,000 years. Running software that was optimized for small group living on African savannas, carrying brains shaped by survival challenges that modern life has rendered completely irrelevant. The fossil record shows this. The ancient genomes confirm it. The bones and the blood speak with one voice. Human biological evolution is essentially frozen, locked in place at the moment when cultural evolution took over the job of adaptation. And yet we've transformed the world beyond recognition. That's the paradox written in bone and blood, the mystery that makes humanity unique among all species that have ever lived. Our bodies stayed the same. Everything else changed. And understanding that paradox is the key to understanding ourselves. But wait, you might be thinking, haven't humans evolved at all in the past 70,000 years? What about lactose tolerance? What about the ability to live at high altitudes? What about all those documented genetic changes that scientists have identified in different human populations? Surely those count as evolution. Surely those prove that natural selection is still operating on humanity. You're absolutely right to raise these objections. And the honest answer is yes, humans have continued to evolve in certain limited ways. The engine of natural selection hasn't completely stopped running. It's still chugging along, still producing genetic changes in response to environmental pressures. But here's what's crucial to understand. The nature of these changes reveals exactly how different post-cultural human evolution is from everything that came before. These recent adaptations don't contradict the argument that human evolution essentially stopped. They illuminate it. Let's start with the most famous example of recent human evolution, lactose tolerance. This is the ability to digest lactose, the primary sugar in milk, into adulthood. It's often cited as proof that humans are still evolving, and in a narrow sense that's true. But examining it closely shows exactly what kind of evolution is still happening and what kind has stopped. In most mammals, including most humans throughout history, the ability to digest lactose disappears after weaning. Infants produce an enzyme called lactase that breaks down lactose in mother's milk. But once weaning is complete, typically by age 3 to 5, lactase production declines dramatically. Adult mammals don't need to digest milk because adult mammals don't drink milk. There's no evolutionary reason to maintain lactase production past childhood, and maintaining unnecessary biological functions wastes energy. This was the situation for all humans until relatively recently. For hundreds of thousands of years, no adult human could efficiently digest fresh milk. Consuming large quantities would cause bloating, cramping, and diarrhea as undigested lactose fermented in the gut. Then, around 10,000 years ago, some human populations began domesticating cattle, goats, and sheep. Suddenly, milk from these animals became a potential food source. Available year-round, renewable, packed with calories and nutrients. But most adults couldn't digest it effectively. The milk was there, but humans couldn't fully exploit it. In this situation, any genetic mutation that allowed continued lactase production into adulthood would provide a significant survival advantage. Access to an abundant food source that others couldn't use, extra calories during famines, better nutrition for children of lactose-tolerant mothers. The selection pressure was real and substantial, and evolution responded. In multiple populations that adopted dairy farming, mutations arose that kept lactase production switched on throughout life. In European populations, a single mutation appeared around 8,000 years ago and spread rapidly through the population. Today, more than 90% of people in Scandinavia and Northern Europe are lactose tolerant. In East African pastoralist populations, different mutations arose independently, producing the same result through different genetic mechanisms. In parts of the Middle East and South Asia, still other mutations appeared. This is natural selection in action. Beneficial mutations arising, spreading through populations, becoming common within just a few hundred generations. It proves that the mechanism of evolution still works in human populations. But look at what actually changed. Lactose tolerance is a single metabolic switch. One enzyme, one function, one dietary adaptation. It doesn't make lactose-tolerant people smarter, stronger, faster, or more capable in any general way. It just lets them drink milk without digestive distress. A person who's lactose intolerant can live a perfectly healthy, successful life by simply avoiding dairy or using lactase supplements. The adaptation matters for nutrition in dairy farming societies, but it has no effect on cognition, physical capability, social intelligence, or any of the traits that define human uniqueness. Compare this to the evolutionary changes that occurred before 70,000 years ago. Tripling of brain size over 2 million years, complete restructuring of the skeleton for bipedal locomotion, development of sophisticated vocal anatomy, enabling complex speech, evolution of extended childhood allowing prolonged learning. These were fundamental transformations that created new capabilities, that built new systems from scratch, that made humans progressively more different from our ancestors with each passing epoch. Lactose tolerance is nothing like this. It's a tweak, a setting adjustment, the biological equivalent of changing a configuration option in software rather than rewriting the code. The core human operating system remained unchanged, only a minor peripheral function was modified. High-altitude adaptation tells a similar story. Populations that have lived at extreme elevations for thousands of years, particularly Tibetans on the high plateau of Central Asia and Andean populations in the mountains of South America, have developed genetic adaptations that help them function in thin air. These adaptations are real, measurable, and genuinely impressive examples of recent human evolution. But again, examining them closely reveals the limited scope of what natural selection is now able to achieve. At elevations above 3,000 meters, atmospheric pressure drops significantly, and each breath contains less oxygen. For most humans, extended time at high altitude triggers a physiological response. The body produces more red blood cells to capture the scarce oxygen. This works up to a point, but it creates problems. More red blood cells means thicker blood, which increases the risk of blood clots, stroke, and other cardiovascular complications. Chronic mountain sickness can develop, causing fatigue, cognitive impairment, and potentially fatal complications. Tibetan populations have lived on the high plateau for at least 25,000 years, possibly longer. Over this time, they evolved a different response to altitude. Instead of producing more red blood cells, Tibetans maintain relatively normal blood cell counts while processing oxygen more efficiently at the cellular level. The key genetic variant, in a gene called EPUS1, affects how the body responds to low oxygen conditions. Intriguingly, this variant appears to have been inherited from Denisovans, our extinct human cousins, through ancient interbreeding. Tibetans didn't evolve this adaptation from scratch. They inherited a pre-existing solution from another human species that had already developed it. Andean populations, who have lived at high altitudes for a shorter period, around 10,000 years, evolved different adaptations. They tend to have larger lung capacities and more efficient oxygen delivery systems, though they also produce more red blood cells than Tibetans do. Different genetic solutions to the same environmental challenge arrived at independently in different populations. These are genuine evolutionary adaptations. They matter for survival at high altitude. But once again, notice what changed and what didn't. The adaptations affect oxygen processing, blood chemistry, lung capacity. They're physiological adjustments to a specific environmental challenge. They don't affect cognitive capabilities, social behavior, technological aptitude, or any of the traits that make humans distinctively human. A Tibetan Highlander and a sea-level European have essentially identical brains, identical capacities for language and abstract reasoning, identical potential for learning and creativity. The differences are in how their bodies handle thin air, nothing more. And here's something even more revealing. These altitude adaptations evolved precisely because culture couldn't solve the problem. You can't invent your way out of oxygen scarcity. There's no clothing for your lungs, no tool for increasing atmospheric pressure, no technique for extracting more oxygen from each breath. The selection pressure remained because no cultural adaptation could eliminate it. Where culture can solve problems, evolution stops. Where culture can't solve problems, evolution continues to operate on the specific parameters that remain under pressure. Skin color provides another example. Human skin pigmentation varies dramatically across populations, from the darkest tones in equatorial Africa to the lightest in northern Europe. This variation evolved in response to different levels of ultraviolet radiation at different latitudes. Near the equator, Intense UV requires dark pigmentation to protect against folate degradation and skin cancer. At high latitudes, weak UV requires lighter pigmentation to allow sufficient vitamin D synthesis in the skin. This is evolution in action. Different selective pressures at different latitudes producing different optimal phenotypes. The changes happened relatively quickly, within tens of thousands of years as human populations spread across the globe and adapted to local conditions. Some of the genetic variants affecting skin colour in Europeans appear to have become common only within the past 8,000 years or so, suggesting ongoing selection even in relatively recent times. But again, what actually changed? Melanin production in the skin, a superficial characteristic literally skin deep. A person with any skin colour can live successfully at any latitude with appropriate behavioural adjustments, wearing protective clothing or taking vitamin D supplements as needed. The adaptation matters for health in traditional environments, but it has no effect on any cognitive or behavioural trait. It's a tweak to one parameter of human biology, not a transformation of human capabilities. The pattern that emerges from all these examples is consistent and revealing. Recent human evolution operates on peripheral systems: diet, oxygen processing, pigmentation, disease resistance, traits that matter for survival in specific environments, but don't affect the core architecture of the human organism. The fundamental systems that make us human, our brains, our cognitive capabilities, our social intelligence, our capacity for language and culture, these haven't changed in any measurable way. Think of it like this. Imagine you have a computer that was built 70,000 years ago but has been running continuously ever since. Over that time, users have installed different software, changed various settings, adjusted configurations for different purposes. Some users live in hot climates and configured the cooling system differently. Some users processed different types of data and adjusted the memory allocation accordingly. The computer has been customized in countless ways, but the hardware is the same. The processor hasn't been upgraded, the fundamental architecture hasn't changed, the machine's basic capabilities, what kinds of computations it can perform, how fast it can process information, what operations are possible and what are not. These remain exactly what they were when the computer was first built. That's human evolution over the past 70,000 years. Configuration changes, software updates, peripheral adjustments, not hardware upgrades, not architectural improvements, not the kind of fundamental transformation that characterized the previous 2 million years of human evolution when brains were tripling in size and bodies were being restructured from the ground up. The exceptions prove the rule precisely because they're so limited. Natural selection still operates where it can, where cultural solutions haven't eliminated the selection pressure, but it can only operate on traits that still matter for differential survival and reproduction. And in a species that has insulated itself from most environmental pressures through cultural adaptation, that leaves very few traits still under meaningful selection. We haven't stopped evolving because evolution stopped working. We've stopped evolving because we developed something that works better, faster, more flexibly than evolution ever could. The minor changes that continue to occur are the scraps that cultural evolution hasn't yet picked up. They're the remnants of a system that once drove all of life on Earth, but has been largely superseded in our species by something unprecedented. Understanding this distinction is crucial. When people say humans are still evolving, they're technically correct but deeply misleading. Yes, gene frequencies are still changing. Yes, selection still operates in limited domains. But the kind of evolution that created humanity, the dramatic transformation of bodies and brains over millions of years, that has stopped. What continues is maintenance and minor adjustment, not innovation and construction. We're biological antiques, running ancient hardware in a modern world, changed in minor ways by recent evolution but fundamentally identical to our Ice Age ancestors. And that fact, properly understood, explains more about the human condition than almost anything else we could learn about ourselves. So let's bring this journey home. Let's connect everything we've explored about ancient catastrophes and genetic bottlenecks and the death of natural selection to the life you're actually living. Because the fact that human evolution essentially stopped 70,000 years ago isn't just an interesting piece of trivia about the deep past. It's the key to understanding why modern life feels so difficult, in ways that seem like they shouldn't be difficult. Why we struggle with challenges that our rational minds know how to solve, but our instincts keep sabotaging. Why we build societies that make us anxious, bodies that make us sick, and lives that leave us feeling vaguely unsatisfied even when we have everything our ancestors could have dreamed of. The answer is evolutionary mismatch. We're running Stone Age software in a digital world. Our bodies and brains were optimized for conditions that haven't existed for tens of thousands of years, and they're constantly being triggered by a modern environment they were never designed to handle. Start with food. For millions of years, calories were scarce and unpredictable. Our ancestors never knew where their next meal was coming from. Finding a concentrated source of energy, ripe fruit heavy with sugar, a honeycomb dripping with sweetness, fatty meat from a successful hunt. These were rare windfalls that might not come again for days or weeks. Natural selection strongly favoured individuals who gorged on these foods when they found them, who craved them intensely, who felt deep satisfaction when consuming them. That craving, that drive to eat as much calorie-dense food as possible whenever it's available, was a survival advantage for hundreds of thousands of generations. Now consider the modern food environment. Concentrated sugars and fats aren't rare windfalls. They're available everywhere, all the time, in quantities our ancestors couldn't have imagined. Convenience stores on every corner stocked with candy bars and soft drinks. Fast food restaurants serving meals with more calories than our ancestors might have consumed in days. Supermarkets overflowing with processed foods engineered by food scientists to trigger exactly the cravings that evolution built into us. Our Ice Age programming says eat it all, now, as much as you can, because who knows when you'll find food like this again. But the food never runs out. The next meal is always available. And so we keep eating, driven by instincts that made perfect sense on the African savannah but are slowly killing us in the modern world. Obesity, diabetes, heart disease, a constellation of metabolic disorders that barely existed for most of human history are now epidemic. Not because humans are weak or lack willpower, but because we're fighting against millions of years of evolutionary programming every time we try to eat sensibly in an environment of unlimited abundance. The same mismatch applies to physical activity. Our ancestors walked miles every day, tracking game, gathering plants, moving between campsites. Their bodies were designed for constant movement, and physical exertion was unavoidable. The reward systems in their brains were calibrated to encourage exactly enough effort to secure survival, not more. Rest when you can, conserve energy when possible, because tomorrow might require extraordinary exertion. Modern life has removed almost all requirements for physical activity. We drive to work, sit at desks, take elevators, and spend our leisure time in front of screens. Our bodies, still running the same programming, interpret this lack of physical demand as an invitation to conserve energy. Exercise feels like work because our instincts tell us it's wasteful to expend calories unnecessarily. The couch feels appealing because rest was precious when rest was rare. But now rest is the default, and our bodies are deteriorating from disuse while our brains tell us we're doing exactly what we should be doing. Consider stress and anxiety. For our ancestors, the threats that triggered stress responses were immediate, physical, and resolvable. A predator appears. Your body floods with adrenaline and cortisol. Your heart rate spikes. Your muscles tense. You fight or flee. The threat is resolved one way or another, usually within minutes. Then the stress response subsides, the hormones clear from your bloodstream and your body returns to baseline. Modern stressors are completely different. Job insecurity, financial problems, social media conflicts, political anxieties, health concerns that won't be resolved for months or years. These threats can't be fought or fled. They persist indefinitely, hovering in the background, triggering low-level stress responses that never fully resolve. Your body keeps producing cortisol as if there's a predator lurking nearby that you need to be ready for. But the predator never appears and can never be defeated. The stress just continues, day after day, year after year, slowly destroying your health in ways that acute stress never would. Anxiety disorders, depression, chronic stress-related illness. These are epidemic in modern societies. Not because modern people are weaker than their ancestors, but because modern life presents exactly the kind of persistent, unresolvable threats that our stress response systems were never designed to handle. We're running fight-or-flight software against threats that require entirely different responses, and the mismatch is making us sick. Social instincts present another profound mismatch. Humans evolved in small groups, probably between 50 and 150 individuals, where everyone knew everyone. Your reputation in that group was your survival. Being liked, respected, and valued by your band members meant access to food during shortages, help when you were injured, protection from external threats. Being rejected or ostracized could be a death sentence. Our brains became exquisitely tuned to social acceptance and rejection, constantly monitoring our standing in the group, feeling intense distress at signs of social exclusion. Now we live in cities of millions. We interact with hundreds of strangers daily. Social media exposes us to the judgments of thousands or millions of people we'll never meet. Our Ice Age social monitoring systems are overwhelmed, constantly scanning for threats and status information in an environment where such scanning is largely meaningless. We feel anxious about what strangers think of us. We obsess over online interactions with people who have no power over our survival. We experience loneliness in crowds because our bonding mechanisms were designed for small, stable groups, not vast fluid social networks. Sleep is another casualty of mismatch. Our circadian rhythms evolved to track the sun, waking at dawn, sleeping at dark, with activity levels following seasonal variations in day length. Artificial light has completely disrupted this system. We can illuminate our homes as brightly as midday at midnight. We stare at glowing screens that emit exactly the wavelengths of light most effective at suppressing melatonin and tricking our brains into thinking it's daytime. Then we wonder why we can't fall asleep, why our sleep is shallow and unrefreshing, why we wake up tired despite spending 8 hours in bed. The list goes on. Our risk assessment systems, calibrated for immediate physical threats, are terrible at evaluating statistical dangers or long-term probabilities. We fear plane crashes while driving casually despite driving being far more dangerous. We worry about rare but vivid threats while ignoring common but mundane ones. Our planning horizons, adapted for environments where the far future was both unpredictable and potentially irrelevant, struggle with challenges that require thinking decades ahead. Climate change, retirement planning, chronic disease prevention, these require cognitive capacities that evolution never selected for. Understanding these mismatches doesn't make them disappear. Knowing why you crave sugar doesn't make sugar less appealing. Knowing why social rejection hurts doesn't make it hurt less. But understanding does create possibilities. It creates the possibility of designing environments that work with our ancient natures rather than against them. It creates the possibility of developing strategies that account for our evolved biases rather than ignoring them. It creates the possibility of extending ourselves compassion when we struggle with challenges that our brains simply weren't built to handle. And now we stand at another threshold, another pivotal moment in the long story of human evolution. For 70,000 years, cultural evolution has been our primary adaptation mechanism, transforming how we live without changing what we are. But new technologies are emerging that might change the game once again. Genetic engineering now allows us to edit the human genome with increasing precision. Technologies like CRISPR make it possible to modify DNA in ways that would have seemed like science fiction a few decades ago. For the first time in the history of life on Earth, a species has the potential to take control of its own biological evolution, to design rather than simply inherit genetic traits. We could potentially eliminate genetic diseases that have caused suffering for millennia. We could possibly enhance cognitive abilities, physical capabilities, disease resistance. We could theoretically reshape the human organism in ways that evolution never would have produced. Brain-computer interfaces are advancing rapidly, promising to directly connect human nervous systems with digital technologies. Neural implants that restore hearing or vision are already in use. Research into more sophisticated interfaces that could enhance memory, accelerate learning, or provide entirely new sensory capabilities is underway. The boundary between biological human and technological human is becoming blurry, and it may dissolve entirely within generations. Artificial intelligence presents yet another possibility for transcending biological limitations. If we create machines more intelligent than ourselves, the entire question of human evolution might become secondary. Intelligence might continue advancing through silicon rather than carbon, with biological humans either merging with AI systems or becoming increasingly irrelevant to the trajectory of intelligence in the universe. We don't know which of these paths humanity will take, or whether we'll find ourselves on paths no one has yet imagined. But we do know that we stand at a moment of profound potential transformation, perhaps the most significant since our ancestors emerged from the Toba catastrophe with the cognitive capabilities that would eventually produce everything we call civilization. And through all of this, through all the technology and transformation and uncertainty about the future, one thing remains constant. We are all family. Every human being alive today, all 8 billion of us scattered across every continent and culture on Earth, we all carry the genetic legacy of those few thousand survivors who made it through the volcanic winter 74,000 years ago. Beneath all the surface variations in skin colour and facial features and cultural practices, we share the same fundamental biology, the same cognitive architecture, the same ancient programming running in our modern brains. The genetic differences between human populations are trivial compared to the differences within populations. A person from Norway and a person from Nigeria share the vast majority of their DNA. They have the same basic brain structure, the same capacity for language and abstract reasoning, the same potential for creativity and compassion. The variations that seem so significant from a cultural perspective are, from a biological perspective, minor adjustments on a common theme. This is the deepest lesson of human evolution. We are one species, one family, all descendants of the same Bottleneck survivors, all inheritors of the same crisis, all proof that culture and cooperation can triumph over blind biological chance. Our ancestors survived the worst catastrophe our species ever faced, not through strength or speed or any individual advantage, but through working together, sharing knowledge, maintaining cooperation under the most extreme pressure imaginable. That capacity for cooperation, for cultural evolution, for solving problems collectively that no individual could solve alone, this is what makes us human. It's what allowed us to stop evolving biologically and start evolving culturally. It's what took us from scattered bands of survivors huddled in African refugia to a global civilization that has touched every corner of the Earth and reached beyond it into space. And it's what we'll need to face whatever challenges the future holds. So here's what I want to know. Now that you understand why human evolution essentially stopped 70,000 years ago, does it change how you think about yourself? About the struggles you face every day? About what connects you to every other human on the planet? Leave a comment. I genuinely read them, and I'm curious what resonates with you. And if this video gave you something to think about, hit subscribe. We're going deep on more forgotten chapters of human history. Sweet dreams wherever you're listening from tonight. And remember, you're walking proof of the greatest survival story ever told. Your ancestors made it through the apocalypse so you could be here, wondering about them. That's kind of beautiful when you think about it.